My proposal covers an improved epidemic model for interconnected networks. The world is more interconnected than ever before. It is now, more than ever, cheaper, easier, and faster to travel internationally. In 2004, global air traffic was 2 billion passengers, whereas in 2019 it was 4.7 billion passengers. However, this increased connectivity is a double-edged sword. Epidemics now spread more quickly and more unpredictably than they did before. For example, the COVID-19 virus traveled to 114 countries within 3 months. Pandemics, whether they be naturally occurring or human-engineered, are a simultaneously likely and severe problem. Research suggests that there is a 38% chance of another COVID-scale pandemic occurring within the average lifetime. Current excess mortality estimates for the COVID-19 pandemic range between 15 million and 27 million deaths. Therefore, it is crucially important that we develop a mechanism with which the role that transport networks and the restrictions upon them play in the development of pandemics can be examined. The model has two main parts, the transport network and the disease transmission dynamics. The transport network is modeled as a directed weighted graph, with each vertex representing a population center, and each vertex being a four-dimensional vector, counting the number of susceptible, exposed, infectious, and recovered people within each vertex. Furthermore, the edges represent the transport between them, and each edge is defined by passenger flow rate and transport unit frequency. The disease transmission dynamics are based upon the classic SEIR model, in which susceptible people come into contact with infectious people at rate C and become infected with probability beta. They then become exposed. The disease incubates within exposed people and they become infectious at rate sigma. Infectious people then recover at rate gamma. However, I extend this model by adding and subtracting the total number of people entering and leaving each vertex, as shown here. On each edge, I say that susceptible people can become exposed to the illness. The exposure rate for susceptible people depends on how crowded each transport unit is, the number of infectious people travelling. We assume that the time spent on each edge is shorter than the incubation and recovery time. Modelling travel restrictions, we want to be able to restrict travel along each directed edge by any amount. We also want to specifically restrict infectious people from travelling. Therefore, travel restrictions are fully defined by two matrices, P and U. For each edge, Uij is the proportion of everyone allowed to travel, whereas Uij times Pij is the proportion of infectious people allowed to travel, where Uij and Pij are both real numbers between 0 and 1. Combining all this together, we arrive at the final post-restriction equations. A full explanation and derivation of these equations is given in the report. To evaluate the cost-benefit of each mitigation strategy, we have to quantify cost and benefit. To quantify cost, we use the disruption index, which is the proportion of people who would have travelled who are restricted from travelling, shown in the equation below. For benefit, we define epidemic spread index, which is the proportion of the population infected by the disease. It is better to minimize both of these indices. Finally, we define the optimization problem, which is to find mitigation strategies, P and U, which minimize disruption given a fixed upper limit for epidemic spread. During the course of this project, I conducted a proof of concept case study in order to show that the model could be used to find optimal mitigation strategies and perform analyses. To do this, I tested the efficacy of 6 different mitigation strategies, as well as the effective response time. The case study was intra-EU civil aviation. I modelled the 10 most populous countries in the EU, although 10 was chosen arbitrarily, and the model is completely scalable, so any number of countries would have worked. The diagram shows the transport network. The thicker the arrow, the higher the passenger flow rate, and the darker coloured the arrow, the more crowded each transport unit. This is what happens when no travel restrictions were placed at all. As you can see, the disease spreads quickly out of Sweden and reaches countries with high passenger flow rates first. This is what happens when an immediate full quarantine of Sweden, the source country, occurs. As you can see, the disease does not spread outside of Sweden. In all, I tested 6 mitigation strategies, each with 5 different response times, and I evaluated their epidemic spreading index, their disruption index, and the overall length of the epidemic in each case. Here are some insights from the analyses. As the model serves as a framework for analysis, the model can help by indicating to where an epidemic might next spread. It can help by predicting how fast an epidemic might spread among population centres. It can also help by evaluating the efficacy of a travel restriction policy, and also help by finding an optimally cost-effective travel policy. In the future, I will improve the model and the simulation. I will do this by considering exposure time using the Wells-Riley model. I will also consider stations and airports as transmission hotspots. Furthermore, I will get in touch with academics and professors to discuss possible improvements to the model. Then, I will find a solution method for the optimization problem, and considerations will be given to the use of a machine learning model. Once that is done, I will develop a software in order to visualize the data from the optimization problem, such that decision makers can easily see what the mathematically optimal travel restriction policy is. Finally, I hope to propose this model to public health officials so that real change can be implemented.